In the last lecture, we have been discussing about the restricted three body problem. So, in this lecture, we are going to conclude this. So, we have started with two primary masses, which were the m 1 and m 2. Okay. In the normalized situation, we wrote this as this mass as 1 minus mu star and this mass as mu star. Okay. The barycenter was shown as B. Okay. So, this distance from here to here, this is nothing but mu star, and distance from here to here, this is 1 minus mu star on the normalized scale. And we took the Lagrangian points on this side as L 3, on this side as L 2, and here we took as L 1. Okay. So, these are the three Lagrangian points L 1, L 2 and L 3, which are lying in a line, and we were trying to derive the equation for the x, which is the distance of the Lagrangian point from the barycenter, okay, from the barycenter, at which also the located is the origin of the synodic reference frame. So, this is basically in the synodic reference frame we are looking for this L 1 distance. So, in the synodic reference frame, this distance is x and also this coincides with the barycenter. So, this distance remains same. So, now given this distance, okay, so we wrote for the Lagrangian point L 3 one equation, for L 2 we wrote another equation, and for L 1 also we wrote on one equation. So, we took an alternative route to describe all these three equations, and besides we were progressing with our earlier model, in which we wrote x is equal to 1 minus mu star times x minus mu star divided by Okay. So, we have started with this equation, and then by putting x is equal to minus x, we solved for the point L 2, and by taking this as it is, we wrote the equation for L 3. Okay. So, we wrote the equation for L 3 by taking x is equal to positive, for L 2 as x is equal to negative. Now, we have to work for the L 3 point, L 1 point. So, for the L 1 point we have, we need to write this as, obviously for the L 1 point, the distance here what we are doing on this side, because x is on this side positive and on this side x is negative. So, for these three Lagrangian points we are writing three separate equations, such that once you solve those equations, so the positive value of x will give the location of L 1, L 2 and L 3. This was our objective. Okay. So, proceeding this way, so on this side x is negative. So, we are going to put here the minus sign here in this place, okay. And similarly, the coordinate of this one is basically 1 minus mu star with a negative sign, or this distance we can write as, and distance from here to here, this distance can be written as 1 minus mu star. Similarly, this distance from here to here, this is nothing but x. Okay. So, to work out for the L 1 point, what we need to do, we put x is equal to minus x, and then we write in the same way 1 minus mu star minus x minus mu star divided by minus x minus mu star whole cube plus mu star times. Now, we subtract from the distance from here to here, this is given to be 1 minus mu star. So, and taking this with a negative sign, okay, we write it in this way. Now, look into the whole thing, how this gets reduced to 1 minus mu star, and this minus sign will come outside, x plus mu star Okay. If you look into this quantity, this x is positive here, this is positive, this is positive, mu star is positive, okay. 1 minus mu star, this quantity is also positive. Okay. Therefore, we can cancel the numerator and the denominator, and we can write this as x plus mu star whole square plus mu star divided by x minus . Okay. This facilitates our derivation of the equation, and if you remember what we did, we cancelled the negative sign on both the sides. So, ultimately the equation gets reduced to 1 minus mu star divided by x plus mu star whole square minus mu star divided by x minus 1 minus mu star whole square. And you can compare this with the equation that we derived last time. So, let us look into that equation. Okay. This is the equation that we worked out for the L 1, okay, x minus 1 minus mu star divided by x plus mu star. You just look into this, both the equations are exactly same, but this equation last time we derived using an alternative route, where we took into consideration the forces acting on the two masses, forces acting on the mass m, which is placed at Lagrangian point L 1 by mass m 1 and mass m 2, and besides, because it is a moving in this way or either this way. So, the necessary centripetal acceleration is provided by the subtraction of the two forces. This is pulling it in this direction, another one is pulling into this direction. So, we subtracted this, and this is the resultant gravitational force provides this the necessary centripetal force to move in a circle. So, using this condition, we worked out last time this equation, and this equation is the same as we have written today. So, this is what we got the last time. So, both the alternative routes you can take, and you can work it out, okay, and there is no difference between these two. So, ultimately the last time what resulted, that we got 3 quintics, which were of the form a 0 plus a 1 x plus a 2 x square plus a 3 x cube and solution of this quintics will give the 3 Lagrangian points. Now, to get these 3 Lagrangian points, obviously, it is not easy to work it out. So, this has to be done numerically. So, this can be solved, this can be solved numerically. So, we do not do the numerical exercise here. So, to work out this, so the 3 equations that we developed. So, this was the third equation, the last equation that we wrote as the equation number G 1, or this can be multiplied, the whole thing denominator can be brought on the left hand side, and then this gets multiplied by this term, gets multiplied by this term, and this term gets multiplied by this term. So, we wrote in a polynomial format. So, after writing in a polynomial format, we got this quintic equation for all the 3 of them. Okay. So, for the first quintic, which we wrote as the equation number E 1, okay, the solution can be written as these coefficients A 0, A 1, A 2, A 3 and A 4, and A 5 here is nothing but equal to 1. Okay. So, A 0 becomes minus 1 plus 3 mu. Okay. Of course, while you are writing this equation in the polynomial format, and after getting the polynomial format, you are getting the x terms with the same degree together, and therefore, these coefficients will appear here in this place, and it has to be done with great patience. So, if you do it, then you get these coefficients in this format. So, for the first quintic, we get A 0 is equal to minus 1 plus 3 mu minus 3 mu square, A g minus 1 plus 3 mu minus 3 mu square. Then we have A 1 is equal to 2 minus 4 mu plus mu square minus 2 minus 1 plus 2 mu minus 6 mu square plus 4 mu cube and A 4 is equal to minus 2 plus 4 mu. So, this corresponds to, see in the last lecture, we have this corresponds to this quintic x times x minus mu square times x plus 1 minus mu square on the, and this equal to this quantity. So, this was our quintic number E 1. Okay. So, for the next quintic, which is E 2, for the second quintic, the second quintic we have written as F 1. Okay. For the second quintic, which is F 1, so x is equal to x times x plus mu star square times x minus 1 minus mu star whole square plus mu star whole square. So, this was our second quintic, and for the second quintic we can write okay, little modification is there, going back to our earlier thing, this stands for F 1. Okay. This is the second quintic, in fact, this is second quintic. So, for the second quintic, this is for the rightmost point which is L 2. And this one we are writing for E 1 here. So, this is the leftmost point, which in our case we have written as L 3. Okay. So, we need to do the modification here in this place. So, we replace this by another term. Okay. So, for the first quintic, now this is our first quintic. Okay. So, for the first quintic, x times x minus mu star square times x plus 1 minus mu star square is equal to 1 minus this is the first quintic, the leftmost point which is L 3. So, for the Lagrangian point L 3 and for this quintic, the solution that we get, we can write as A 0 remains same. So, A 0 as we have got for the second quintic. So, A 0 will be minus 1 plus 3 mu minus 3 mu square, and A 1 will be changed minus 2 plus 4 mu square minus 2 mu cube plus mu to the power 4. A 2 is also changed. So, we have A 2 is A 1 is changed, A 2 is changed, A 3 remains same as for the second quintic. Okay. And again A 4 will change, this is 2 minus 4 mu. Okay. Now, for the third quintic, okay. So, the third quintic we have written as x times x minus mu star, this is third quintic is this is plus x times x plus mu square times x minus 1 minus mu star whole square, this is equal to 1 minus mu star times minus mu star times whole square. So, this is our third quintic, this is the intermediate Lagrangian point, Lagrange point, which we have written as L 1. Okay. So, for L 1 the solution that we get, this is A 0 equal to minus 1 plus 3 mu minus 3 mu square plus 2 mu cube, A 1 equal to 2 minus 4 mu plus 5 mu square minus 2 mu cube plus mu to the power 4. 4 mu cube, and then now in these coefficients which are written in terms of this mu star, all of them are, this is mu star. So, all of them are written in terms of mu star. So, the earlier equations also we have written, they are all in terms of mu star. So, all these are mu stars. Okay. Here too these are mu stars. These are mu stars. So, one caution must be taken care of. Say what we have written here, this is our point m 1, and here the mass m 1 is there, another mass m 2 is there, and the mass of this we have written as 1 minus mu star, and the mass of this we wrote as mu star, and from the origin of the synodic or the barycentric reference frame, the distance we wrote as this as mu star, and from here to here the distance we wrote as 1 minus mu star. So, instead of doing this, if you replace the same thing as m 1 m 2, and here the mass, then the normalized scale you write this as mu star, and this one you write as 1 minus mu star. Okay. So, obviously, this distance then will become 1 minus mu star, okay. And the distance from here to here, this will become mu star. Okay. So, if you replace it with this, so the coefficients of this quintics that we are writing here, so the sign of them will change. Okay. So, this must be taken care of. So, if you do the mistake here, then so obviously, it will not match with this. So, this must be taken care of while developing the equations of quintics. So, a mistake in this, it will totally give you the wrong values of the Lagrangian points. So, once we have done this, now this quintics can be solved only by some numerical procedure. So, we avoid that, because this is the last lecture on the restricted 3 body problem, and this scope of this course is limited in this respect. Okay. So, we can take some example and we can show the how the L 4 and L 5 at least can be calculated. So, say we have the earth moon system. For the earth moon system, the earth has a mass of 5.974 10 to the power 24 kgs, and this is the mass of earth, and mass of moon, this is 7.3483. Okay. So, mu star can be written as, mu star is nothing but mu 2 by mu 1 plus mu 2, means we have written this mu 2 is equal to g times m 2 divided by g times m 1 plus g times m 2. Okay. So, m 2 here is stands for moon. and M1 stands for earth. So, G cancels out and this simply becomes M2 by M1 plus M2. Okay. And if you insert these values, so 5.97, this is 7.3483 into 10 to the power 22 divided by 7.3483 into 10 to the power 22. Okay. And this value will approximately turn out to be 0.01214. So, this is mu star. Okay, now, for calculating Lagrange points L4 and L5, this is mass M1 here, this is mass M2 and this is the point L4 say. So, we know this is root 3 by 2 on the normalized scale, okay, and on the non normalized scale. So, this is the distance r12. So, this becomes r12 and this distance from here to here, this is nothing but r12 and this is also nothing but r12. These angles are 60 degree. Okay. So, it is a very easy to work out where this L4 will depend if the distance r12 is known to us. Okay. Now, if for the earth moon system, if we have earth here in this place and suppose the moon is present here in this place. So, L4 and L5 they together make the equilateral triangle with respect to this earth and moon. So, we have the equilateral triangle which is present like this. So, this is our L4 and this is L5. Okay. And if you remember, the barycenter is lying very close to the earth. So, if the barycenter is lying here, okay, so the whole thing this is moving about this barycenter, and if you look into the motion of the moon with respect to the earth. So, with respect to the earth, moon will keep moving like this, okay, say in the circular orbit it is moving like this. So, if it is moving like this, so simultaneously the barycenter which is a inertial point. Okay. So, the earth moon system, the earth is and the moon both are moving about this barycenter. Okay. So, the moon motion it appears to be with respect to earth, it is lying on a nothing but a circle. So, as the moon moves on the circle, so you will see that the Lagrange points L4 and L5 they will also keep lying on this circle. Okay. Now, what about the point L1? So, L1 point, suppose this lies here and we have the L2 point that we have written which lies here on this right hand side, and L3 point it lies little short of this point. Okay. So, say this lies here in this place, this is too much magnified on this scale to keep the clarity. Okay. So, the distance between the earth and the moon. So, we have this distance, this is 384,400 kilometers. So, this distance also then becomes 384,400 kilometers, okay, and this distance also this will be the same. Okay. So, this distance are equal. This point will lie at a distance of 64700 kilometer, and the point L1. So, this distance from here to here, this is 58400 kilometer, and the distance to the L3 point from the earth, this is 381,600 kilometer, okay. While the distance between this and this point from earth and this is nothing but the radius of the orbit of the moon. So, this is 384,400 kilometers, okay, and the barycenter which is lying here. So, it falls at a distance of, this is around 4670 kilometers. Okay, so, this gives you a nice picture of how the Lagrangian point, 3 Lagrangian points are, Lagrange points are lying with respect to the earth and moon. So, as the moon is moving around the earth or with respect to the earth, actually both are moving about their barycenter, but from the earth we can see that the moon is moving around the earth. So, if we take this relative motion, so the Lagrange points L4 and L5, they will appear to move on this circle, and L3 lies little inside this circle. Okay. Now, the as already we have discussed that the L4 and L5, these are the stable points. So, proving the stability of this system is again beyond the scope of this course, okay. But rigorous analysis can show that for the once we are working for these Lagrange points. So, if mu star this is less than 0.0385, okay, then the L4 and L5 will be, or say the Lagrange points will be stable. Rather than writing L4 and L5, then the Lagrange points are stable. So, in this case only L4 and L5. Okay. So, for the earth moon system, just now we have calculated that mu star is nothing but 0.012145. So, this is less than 0.0385, and therefore, L4 and L5 they are stable Lagrange points. So, this implies that if you put any object at L4 and L5, so it will remain, it will appear to be stationary with respect to the earth and the moon. Okay. So, means this will maintain a equilateral triangle, but in reality what happens, because of the perturbation of the sun. Okay. So, really this point needs station keeping, means you have to provide from time to time some thrust, say if you are putting some satellite. So, it will try to deviate from this point. So, you need to do the correction by giving appropriate amount of thrust. Okay. So, without thrust you cannot keep the satellite in these 2 points, even for the earth moon system, because the naturally the perturbation of the sun is present, while the L1, L2 and L3 they are the unstable points, and obviously if you want to keep the objects in this place, then you definitely need the station keeping, and besides the sun perturbation is already there. Okay. So, for the sun earth system, we have sun mass as m sun, we can write as 1.989 into 10 to the power 30 kg, and m earth we already know that this is 5.974 into 10 to the power 24 kgs. Okay. Therefore, mu star in this case, this will be approximately 3.00 10 to the power minus 6, and obviously this quantity is much less than 0.0385, and therefore, L4 and L5 are stable in this case also. Okay. So, earlier NASA has sent some satellites, and it has tried to utilize this Lagrangian points, Lagrange points for doing the astronomical observation. So, solar observation spacecraft has been placed at L3. So, L3 is present between these two masses, M1 this is sun, and here this is M2. So, this is earth. So, L3 is present here in this place. Now, L3 we have taken in this case. Okay, we have taken here as L1. Okay. So, to observe the sun, so satellite has been put here in this place, but obviously this requires station keeping, and this distance is around 1.5 million miles from Earth. Okay. And similarly, L2 also it lies around at the same distance, little bit difference is there. So, this also lies around at 1.5 million miles. This is million kilometers, sorry, this is kilometers, million kilometers. 1.5 million kilometers on this side and 1.5 million kilometers on this side. Okay, and L3 is lying here. Okay, so, for calculating all these distances, if we solve the solve these equations numerically, so all these distances can be found out. Now, in the case of the Earth Sun system, the distance between the Earth and the Sun. So, this distance from here to here, this is around 6.9599. Sorry, this is the mean radius of the Earth. This is 1.495978 into 10 to the power 8 kilometers, and this is nothing but 1 astronomical unit. Okay, the distance between Earth and the Sun, this is taken as 1 astronomical unit. So, if you take this distance and you know this is 1.5 million miles million kilometers. So, you can see how large this distance is. So, it is almost near the Earth, while this point is far more away. Okay, so, next we can look little bit more into the equation for the x. So, the x for the L4 and L5, we wrote this as r 1 by 2 times mu 2 minus mu 1 by mu 2 plus mu 1, and on the normalized scale the same thing will appear as r 1 2 will be written as 1 and this is 2, and the whole thing then you can mu 2 by mu 2 plus mu 1, you can divide it, and this quantity is nothing but your mu star, okay, and then you have mu 1 by mu 2 plus mu 1, this quantity is nothing but 1 minus mu star. So, what you get here 1 by 2 mu star minus 1 minus mu star. Okay, so, this becomes 1 by 2 mu star minus 1. So, this is mu star minus 1 by 2. So, x is given by this value. So, this is the location of L4, L5 on x axis, and obviously the y on the normalized scale you can write y as this capital Y, and this is nothing but plus minus root 3 by 2. Okay, now we can proceed to our Jacobi integral. So, we got the Jacobi integral in this format. So, again on normalized scale, which we on normalized scale. So, we wrote omega is equal to 1 and mu 1, obviously then we are writing as 1 minus, this is equivalent to 1 minus mu star, and mu 2 then becomes equivalent to mu star. Okay, so, then this equation gets reduced to x square plus y square plus 2 Now, we know that v square, this is a positive quantity, or at most it can be 0, and therefore, this implies that s square y square plus 2 times 1 minus mu star by r 1 plus 2 mu star by r 2 minus c, this will be greater than or equal to 0. Okay. Or x square plus y square Okay. So, the equality sign when x square plus y square to 1 minus mu star when this equality sign holds means v equal to 0. This implies v equal to 0. So, already we have discussed in the last few lectures that this represents a surface. Okay. So, when v equal to 0, so we have x f x y z is equal to c. This describes a surface. Now, it is a very interesting to see here z is not present of course, in this case because we have put z equal to 0. So, if we have z equal to 0, so we are looking in the x y plane. So, we have x here and y here, or either in our case we have plotted x on this x and x s and y x on this x, and this is the negative side of this. So, x is negative here on this side, this is positive, on this side we have written this as positive. So, this f x y equal to c, which is describing a surface. So, now look into the equation for the f x y. This is x square plus y square 2 times 1 minus mu star by r 1 plus 2 mu star by r 2, and this is equal to c. sorry. So, we have different cases we can consider here. We can consider a case, let us say one by one discuss all of them. So, case 1, C is very large. So, this can happen in the following ways: either r 1 tends to 0, r 1 tends to 0, therefore, if tends to 0, this whole quantity will become very large, or either r 2 tends to 0. Okay. Here this quantity r 2 tends to 0, therefore, this quantity will become very large, and the C is x square plus y square itself tends to infinity. Okay. If this happens, okay, so what you get? This is the surface, let us say C equal to C 0, once this quantity equal to C 0. So, this is very large quantity, okay, and you have the points here, say m 1 and m 2, which is present here. So, if r 1 tends to 0, means the point is lying near to this m 1, and r 2 tends to 0. So, point is lying close to m 2. Okay. So, so for a finite large value of C, for a finite large value of C, okay, you can see from this place that if we are not taking, the point is either close to this or either close to this. So, depending on the value of C, value of r 1 will depend. Now, 1 minus mu 1, this quantity is larger than mu star, okay, because the left hand side this mass m 1 we are taking as the larger mass. This is our 1 minus mu star and this is mu star. Okay. So, this is larger mass. So, this implies that for the C, we have to now equalize the left hand and the right hand side, and if we are close to this. So, obviously, we can equate them, and if you equate, okay, so r 2 is from here to here, this distance is quite large. Okay. So, if you look if your mass is close in the vicinity of this, okay, lying somewhere here. So, this distance will be quite large as compared to this. So, this will be so, equate for a finite value of c. So, let us go on the next page 11, 16. Let us say this is C 0. Okay, so, if the mass is in the close vicinity of the small mass is close vicinity of m 1. So, the distance from here to this will be quite large. So, the contribution of this quantity to this C 0 will be very small, and obviously, in this case x 0 x square y square also that will contribute less, and therefore, this will be totally decided by the quantity which is present here. So, depending on the value of C 0, this R 1 radius will be decided. Okay. Similarly, if the mass is in the close vicinity of the m 2, so this will not contribute much, this will not contribute much. Okay. In the close vicinity, this is going to sorry, in the close vicinity, this is contributing, this quantity is contributing in close vicinity, but once the particle is on this boundary where c equal to c 0. So, in this place x square y square is not contributing, while once it is here. So, then it will tend to contribute, but if the mass is say that this mass is very large as compared to this mass. So, again this quantity x square plus y square. So, here the barycenter is lying quite close to this one. So, this quantity will add a small, okay, while this quantity, because this R 1 is small. So, this quantity is going to add less. Yeah, this quantity will become large, and this quantity this quantity will become large, and this quantity will become small, and this is also not very small, but this contribution still is there. Okay. So, from here now we can draw the a circle around this. Let us say this is one circle drawing, another circle I am drawing like this. Now, we can see that the radius of these two circles are, this one is larger and this one is a smaller. This will be very clear from the this equation that we are considering here. Now, this mass is small. Okay. So, this mu star is small, okay. And therefore, to match it with the C, the R 2 also must be small. Okay. This mass is 1 minus mu star, this is quite large as compared to this. In the case of Earth Moon system, you can see that m 1 is around 81 times greater than m 2. So, that simply implies that if this is large and if you have to match with C equal to C 0. So, our R 1 also must be large, and therefore, this is the reason that this radius is shown to be large than this radius. Okay. In fact, this will I have exaggerated this figure. In fact, this will be quite small. Okay. As you can look into this figure, here this radius is quite large and this radius is quite small. Okay. So, here on this also C equal to C 0, and here on this also equal to C equal to C 0. So, we have not done it to the scale. Okay. Now, the region we have drawn here. So, the region inside this region is not permitted. Outside this, V square is greater than 0. Okay. On this, V square equal to 0. Okay. Similarly, on this, V square equal to 0, on this also V square equal to 0. Okay. Inside this, V square is greater than 0, in this region, the region which is shown here. So, this region, this is V square is less than 0. Okay. So, obviously, because V square cannot be less than 0. So, the shaded region shaded by the red ink, it is not permissible, and it is very easy to see using this equation. If you look into this, so you will find that only the shaded region, it is not possible. So, the particle can be either inside this or either inside this or either it can be outside this. It cannot penetrate this boundary. Okay. So, now as we decrease the value of the C, okay. So, after decreasing the value of the C, the two circles which are appearing here as a oblate because of this particular term, this makes it not a exactly circle, but rather than a oblate. So, these two terms together, this is the equation of a circle about the barycenter or the origin of the synodic reference frame, and these are the quantities which will not make it the whole circle, but rather it will look in this fashion. So, as you expand this, as you increase the value of the decrease the value of the C, means here we are considering now a value of C which is less than C 0, let us say C equal to C 1, which is less than C 0. So, in that case, again you will see that this circle this around this is the circle. So, this will expand and this will also expand, and they will merge somewhere, touch each other in some point, which we now call this as the point L 2. This is the Lagrange point. Okay. So, in this is the first development which takes place, which is the Lagrange point L 2. Next, as we further decrease the value of the C, so which is indicated here by C 3, okay. These two oblates they merge together and then open up. Okay. So, now the particle can be inside anywhere this white space, okay, but we are not sure where it is lying, but it cannot cross the boundary. So, this does not tell you where the particle is lying exactly, but it is somewhere inside this boundary, because this by using this equation we are basically defining the boundaries, not the orbit of the particle. So, this merge then the particle can move from this space to this space also. So, it is a permissible. Okay. Now, as you further expand it, so you can see that it touches the outer boundary. So, the L 3 the here in this case it is written as the L 3, the notation is different here. This is taken from the Archie Roy book. So, you can refer to this for this figure. Okay. So, Lagrange point L 3 develops. If you further do that, further decrease the value of the C. Okay. So, after decreasing the value of the C, the L 1 points then develop. Okay. If you further develop, so this annular shaded region which is there, this becomes shortened and it becomes like this. So, if you keep decreasing it, so L 4 and the L 5, these Lagrange points they appear. Okay. So, this implies that now the particle can occupy all these space. Okay. Here the particle can occupy all this white space. Okay. Here the particle can occupy all this white space. So, as the value of the C decreases further and further, so this L 4 and L 5 they will be accessible. Okay. Thank you very much. We continue in the next lecture. So, this is almost cleared, and whatever is remaining we will brief in the next lecture, and then we move on to the finally the trajectory transfer. Okay. Thank you very much.